Thanks for joining back. I'm sorry for if I'm a bit slow. It's because I'm using Google Docs. I'm used to MS Word, but my MS Word was crashing. So I decided to present the lecture on Google Docs. And I'm not so used to Google Docs. So that's why when I was typing, I was typing very slowly. So sorry about that. So that's the general trend. So given a particular polynomial, so given any polynomial uh, you want to interpolate. So given the number of points, you need a specific number of polynomial. Then that's what I've just explained is the general trend of how to get the coefficients in order to get the polynomial that you use to interpolate for the unknown value. So in this question, we are giving, how many points are we giving? 1, 2, 3, 4. We are giving 4 data points. So definitely we can use, for 4 data points, we can use a third order polynomial. Since we have 4 data points now, and obviously we are going to be much more accurate. So we are giving x naught is equal to 1, x1 is equal to 4, x2 is equal to 6, x3 is equal to 5. Then we are giving the value of the function at this value of x. And we want to be able to calculate for x is equal to 2. So simply put, we are using a third order polynomial. So we're using a third order polynomial because we have 4 points. So if you have 4 points, you can use a third order polynomial. If to say we're giving 5 points, is a fourth order polynomial we can derive. If we're given 6 points, is a fifth order polynomial we can derive. So we want to first of all derive the polynomial, the third order polynomial. So this is the general structure for the third order polynomial. So this is the B0, B1, then your B2. So this is the general structure of the polynomial. So you have B0, B1, and B2. So for the second order polynomial, this one is supposed to be B2. Then this is going to be B3. So for a third order polynomial, we are giving 4 data points. So for a third order polynomial, we need to get B0, we need to get B1, we need to get B2, and we need to get B3. You have 3 coefficients we want to derive, and it's of these 4: x B0, B1 x minus x0, B2 x minus x0 multiplied by x minus x1, and B3 x minus x0 multiplied by x minus x1 multiplied by x minus x2. So we need this to get B0, B1, and B2. And for B0 is simply f of x0. So B0 is simply equal to B0 is simply equal to f of x0. So f of x0, and f of x0 is given to us in the question. So we don't need to do anything. So we need to get B1 now, we need to get B2, and we need to get B3. So in order to get these coefficients, we need to, because we are using Newton's finite divided difference. So we need to get the first divided difference, the second divided difference, and the third divided difference, because we're using a third order polynomial. So for a third order polynomial, we need to get the first divided difference, then you need to get the second divided difference, then the third divided difference. Then the values of, so this is going to be your B. You already have B0, so no need to calculate that. So this is going to be your B1, this is going to be your B2, and this is going to be your B3. So the first value of the first finite difference is your B1. The first value of the second divided difference is your B2. The first value of the third divided difference is your B3. But first of all, you need to calculate the first, the second, and the third divided difference. So for the first divided difference, we need to calculate for fx1, fx0. We need to calculate fx2, fx1. Then we need to calculate fx3, fx2. So we cannot do fx4 and fx3. So the next one should have been fx4 and fx3. But this is a third order polynomial, and we're not giving this should have been the next one, but we're not giving x4. We're not giving x4. So we don't have x4 because we are giving 4 data points. We have x0, we have x1, we have x2, and we have x3. So these are the values of the first finite divided difference you can calculate. So as I've said previously, fx1, fx0 is simply given by this, and when it's evaluated, you have 0.46. Fx2, fx1 is simply given by f of x2 minus f of x1 divided by x minus x1. Then f of x3, x2 is simply f of x3 minus f of x2 divided by x3 minus x2. So you can see the trend. So there's no need to memorize anything. There's like a trend going on. Then when you put in the values, because these values are given in the question, you arrive at this particular coefficient. So we can't do this because we don't know x4. But I want to ask, if to say we're giving x4, so what's the formula to calculate f of x4, x3? So in the chat, somebody should type in the formula. For instance, if we wanted to calculate the fourth order polynomial, and for the first divided difference, if we needed this, in this question, we don't need this, right? But if to say we have needed this, can somebody type it in the chat, the formula to calculate this based on what you can see here? That's my question. So I want to know if you're following. So what would have been the formula for this? Though we don't need it because we're not giving because we're not giving x4. Okay, all right. I can see it. Okay, yes. Those people that have replied me, your answer is very, very correct. So based on this, let me just, okay. Yes, thank you all for replying. Thank you. So based on this, like you have rightly said, the value, there will be x4 here. So there will be x4 here. There will be x3 here. Then there will be x4 and there will be x3. So all of you were right. Thank you very much for that. So this is the first finite divided difference. Remember, we are doing a third order polynomial. So we need the first, we need the second, and we need the third divided difference. So for the second divided difference, we need this f of x2, x1, x0. Then we need f of x3, x2, x1. So the equation to calculate f of x2, x1, x0 is simply f of x2, x1 minus f of x1, x0 divided by x2 minus x0. And the formula to calculate for f of x3, x2, x1 is simply f of x3, x2 minus f of x3, x2, x1, then x3 minus x1. So we already know this one, this highlighted f of x2, x1. We got it here. So this is the value. Then f of x1, x0 is this value we got here. Then f of x3, x2 is this value we got here. So as you can see, I told you that you need to calculate for, because what we are after is just the coefficients, B1, B0, B1, and B2. So this is our B0. This one is our B0. This is our B1. You might, at first, you say that why do we need this and this? If to say we've not calculated this and this previously, and this is our B2. So for B2, you need to know this value and this value. That's why we needed to calculate it. So that's why we needed it. So I'm asking, you can see the general trend now. So to calculate for, so similar to what I asked, if to say it was a fourth order polynomial I want to get, we're going to need this value. We're going to need this value. So what is going to be the equation for this? So type it in the chat if you know it. What if to say wanted to calculate for this function of x4, x3, x2. So look at the trend. You need x3, x2, x3, x2, then x2, x1, then the first minus the last. Okay. All right. F of x4, x3, x3, x4. Yes. Yes. Thank you. Yes, thank you. Thank you very much for those of you that have replied me. Thank you. It shows that you are following. So as you rightly said, so this function here is going to be okay. Okay, Patrick, you corrected yourself. Okay, yeah, that's going to be the equation. Thank you for replying. So okay, other people are replying. So thank you for that. It shows that you are following me. So this is going to be, like you rightly said, there will be an x4 here, then this will be x3, then there will be x3 here, there will be x3 here, then there will be x2 here, then this will be x4 minus x2, as you rightly said. So thank you all for those that replied. Then for the third divided difference, you need f of x3, x2, x1, x0. So to calculate that, we needed this. So, and we got, this is f of x2, x1, x0. We already have it here. So you just put in the value here. And this is f of x3, x2, x1. So we got it here. So we just put in the values here. Then you have this. So the question says we should fit a third order polynomial. So like I said, all we are just, in order to calculate these divided differences, the first, second, and third, all we want is B0, B1, B2, and B3. That's all we are after. And B0 is f of x0. We are giving it the question, so no need of calculating it. Then this is your B1. Your B1 is simply the first value of your first. So this is our B1. But we needed to get this and this, because if we want to get for B2, we need this and this. That's why you still need to calculate it. Then this is your B2. This is your B2. The first value is your B2. Then your B3 is this one. So this is your B3 here. So this is the so we've already calculated, we've already gotten B0, B1, B2, and B3. So now all we now can now develop the third order polynomial using this equation here. We can get the third order polynomial. So using this equation, so let me just copy this equation. So this is the equation we need. So we have everything we need. So here is this one is B. Let me just delete it. So here is B3. Then here is B2. So this is B2. Let me just delete it and replace it with B2. Then this is B1. So let me delete it and replace it with B1. And this B1. Then this is B0. Let me delete it and replace it with B0. Sorry, I'm a bit slow. I'm not used to Google Docs. Okay, so we already have B0, B1, B2, and B3. So we can just put in the values we got to write the polynomial. So this is the polynomial we have been trying to derive, and we finally derived it. So we need, the question says we should calculate for the value of the function at x is equal to 2. So in place of x, we're just going to replace it with 2, 2, 2, 2, 2, 2, and 2. So you just evaluate this algebra. And when we did the evaluation, we arrived at 0 point. Sorry, it cut. The formula cut. I don't know why. So I don't know how to bring it back. So this is actually f of x. So this is what we got. 0.6, 0. I don't know why it's being this way, but f of the value we got, copy, is, I don't know, it's not responding to my, okay. The value we got is actually f of x2, copy, is equal to 0.6287686. So this is from this algebra. When you do this algebra, the highlighted equation, this is what you're going to get. Sorry, the equation cut. So you can calculate for the true error. This is the true value we're given in the question. So the true error is at 9.3. So if you can see, when we used a second order polynomial, this question is a third order polynomial. When we use the second order polynomial, we derived, and the error we got was zero. We got, what was our error? Our error was 18%. So now when we used a third order polynomial to fit in the value of the known to get the curve we want, in order to interpolate the value we don't know, the value of the function we don't know, the error like reduced by half. So it's really, is now 9%. So like I said, the more the number of points you have, the higher the order of the polynomial you can fit into it, and the the more accurate your result is. So that's the first method we used is Newton's finite divided difference. So this is the first method, Newton's divided difference interpolating polynomials. So we are going to use the second method. The second method is much more straightforward. It's the Lagrange polynomial. So Lagrange interpolating polynomials. So the Lagrange interpolating polynomial is that to develop um, the polynomial, or to interpolate the value you want. This is the um, general expression of the equation you derive. So where n is the order of the polynomial you are given, or the order of the polynomial, then this is the general function. So to calculate the value of x, which is unknown, this is the general expression for it. So it's the summation of Li of x multiplied by f of xi. Then this Li of x is given by this. So this symbol, this pi, it simply means the product. It simply means the product starting from j is equal to 0 to n, where j is not equal to I. So for instance, now, if we want to, so this is the general structure. So the first method we did was Newton's divided difference method. But we want to use the Lagrange method in order to interpolate, in order to develop the polynomial. So for instance, now, this is the general expression where n is the order of the polynomial. So for instance, if you, to fit a first order polynomial, that's a linear line, is simply, this is going to be given by, so now n is equal to 1. N is equal to 1. Yeah. So it's simply from I is equal to 0 to 1, because n is equal to 1. So this equation 16, when n is equal to 1, becomes this. So L of x0, comma f of x0 plus f L of x1, comma f of x1. So in this case, it is when n is equal to 1, that's a first order polynomial. So this is going to be the Lagrange form. So if it's a second order polynomial for the Lagrange, it's going to be, so now you want to fit a second order polynomial. Now n is equal to 2, f of x2, then L of x0 of L naught, then multiplied by f of x0 plus L of 1 of x, then f of x1, then plus so the last one is going to be L2 of x, then f. So I'm just showing you the general structure. So if it was a second order polynomial, so this equation becomes this. So if it was a third order polynomial, you're going to add an extra 10. So there's going to be an extra 10 here if it's a third order polynomial. So to get L naught, so for instance, to get L naught here, so L naught of x is simply this. is simply this formula here. So this represents a product. It represents a product from j is equal to 0 to j to n. But since n is equal to 1, so here is just going to be, so for L naught, it's simply going to be x minus x. So j will start from 0, then x I, because I is 0. So you have x0 here. Then here is going to be x1, and here is going to be x1. Here is going to be x1. That's for L naught of x. So for L1 of x, let me put L1 of x. L1 of x is simply going to be here. L1 of x is going to be x minus x naught divided by x1 minus x naught. Yeah. So is that case because this is the general structure, right? So you have x here, which is the x here. So for xj, remember that j starts from 0 to n, but your n is 1, and j should not be equal to I. So when you have j is equal to 0 here, so you have j must not be equal to I. So in place of j here, you are going to put, for L1, you are going to put 0. Then for xi, you're going to put 1. So that's the general structure. So this is the Lagrange polynomial. For x, for a first order, this is the form, like I said. For a second order, this is the form. So the number of terms would increase like that. So this is the general structure for finding L of x. So like I said, for the first order polynomial, this equation here becomes this, where L naught is given by this, then L1 is given by this. Then for a second order polynomial, this is the expression for the polynomial based on the method or the Lagrange polynomial. Then L naught is given by this, L1 is given by this, and L2 is given by this. If you can see, there is a general trend. For L naught, is simply x minus x1, x2, x1, x2. So you have L naught here. So there's x naught and x naught. For L1, you have x1 here, you have x1 here. For L2, you have x2 here, then you have x2 here. Then let me just tell you the trick for getting it based on this. So for L naught, like I said, you have x naught, x naught. Then the other expression you have is 1 and 2, 1 and 2. So since this one is 0, x naught, the others is 1 and 2. The others are 1 and 2, 1 and 2. So for L1, so since you have x1 here and you have x1 here, the others are 0 and 2. So you have 0 and 2 here. So for L2, since you have x2 here, x2 here, the others are 0 and 1. 0 and 1. So using this method, you can use it to get the third order polynomial. So let me try to do the third order polynomial from the Lagrange method. So for the Lagrange method, for the third order polynomial, f of x, comma, f of x2. So here you have x3. That's for the third order polynomial. So n is equal to 3. Then you have a last term because it's a third order polynomial. So you have a last term here. And so here is going to be 3. And here is going to be 3. So L of x naught. So it's simply going to be, so here there will be a third term. There will be a third term here. So here is going to be, sorry, I'm not used to, I'm not used to this. It's giving me some issues. So here is going to be x, there's x minus x1, here's x minus x2. So here is going to be x minus x3. That's for the third order polynomial. So here is 3. Then here is going to be, so you have x naught. So here is going to be, sorry, I can't really write it. So here is going to be x1, x2. Then here is going to be x3. But here is x naught. I'm trying to copy x naught. Copy. So here's x naught, supposed to be subscript. Yeah, x naught. So here is going to be x naught. Sorry, I'm very, very slow. It's okay. So this is for the first term. So for the second term, so here is x. There's going to be x naught here. There's going to be x2, and there's going to be x3 here. So this one is going to be x minus x3. So I'm having troubles copying and pasting. So here is going to be x minus x3. Then below is just going to be x. So in place of x1, there's going to be, yeah. So here is going to be x3 in place of this x2, x3. So for the third coefficient is x minus x naught, x minus x1. Then the last one is going to be x minus x2. Then I'm a bit slow, so you can just look at general trend. So here's x minus x2. Then for the denominator, it's going to be x2 minus x3. X2 minus x3. So here it's supposed to be x3 because we are on x2. Then this for the first term, second term, this is the third term. Then there should be a last term. because for a third order polynomial, you have 4 values. So for second order polynomial, you have 3 values. So there's going to be this here. There's going to be a last value here. Then in place of x, in place of this, you put in this. But instead of x3 here, you're going to have x2. You're going to have x2 here. Then you're going to have x2 here. Then here is going to be x3, x3, x3. So this is the general structure. So if you look at it, you will see a trend. So I was trying to describe the trend when I was doing all of this. So I was slow. It's because of I'm not used to typing here. It's giving me some issues. Okay, so we are going to go to a question. So the first method was the Newton's divided difference. So we are going to use the Lagrange polynomial for the first and second order to estimate ln 2. So we have these values. These values are given to us in the question. So we want to use the first order polynomial, first order Lagrange and second order Lagrange. So this is the formula for the first order Lagrange. So simply putting all these values, so all these values are known and given in the question. You have 0.462. Then using second order Lagrange polynomial, this is what we derived, the equation we derived. So putting all the values, and the values are given to us in the question, you arrive at this. So if you compare your results with the method, we first of all used Newton's divided difference polynomial. So if you compared what we got for the linear polynomial in the first method and the second order polynomial in the second method, you will see that the results are the same thing. So the first method or the second method, you arrive at the same value. So in order to do the third order Lagrange, you can just use this this expression I derived just now. So it's actually simple. Once you know the first order form, to get to the second order and third order is going to be a piece of cake. So you can also do it, and if you do it, you're going to confirm that what we got, you're going to arrive at this answer. It's going to be the same answer you obtain using the Newton's divided difference method. So we are going to go into bilinear interpolation. So I would end the meeting.